Okay. So last time we talked about projective Nullstellensatz. As a last thing, just want to finish what I have to say about that. Let me just state it again. So if so let E be an ideal in n plus 1 variables, homogeneous ideal, then we have that the zero set in projective space is empty if and only if I contains all homogeneous polynomials of degree n for some n. For some n of degree maybe large n for some n. And if it's not empty, then we have the usual formulation, namely if the zero set is not empty, we have that the ideal of the zero set of I, so the homogeneous ideal, is equal to the radical. So we showed this. As a consequence of this, we can again show that a projective algebraic set is irreducible if and only if its ideal is a primary. So let me do this. So first, the projective algebraic set X MTN is irreducible if and only if the ideal of X, so which is, I write here again, the homogeneous ideal obviously, is a primary. And the second statement is that if f in K0 n is irreducible, then indeed the zero set of f in Kn is irreducible. So the proof of the second statement is the same as before. Once you know that if the homogeneous ideal is a prime ideal, then the algebraic set is irreducible, then we know that we had seen before that if f is irreducible, then it generates a prime ideal, and so therefore the zero set of f, which is also, so it's a prime ideal, it's a maximal ideal, so that means the ideal of the zero set of f is the ideal generated by f, and so that would be a prime ideal, and this therefore it follows from what we had before. So we only want to show one. So we had the same proof in the defined case, there's no difference. So there are two directions. So assume that X be irreducible. This is the nice easy direction. So that means we can write X, no, reducible, I want it, not irreducible. So this is therefore, I think, the other direction. Let me see. So if X is reducible. We want to show that the ideal is not a prime ideal. I think that means it's in this direction. Let x be reducible, then we can write x is equal to x1 with x2, where the xi subset x are closed and both different from x. So now it follows that if I take the cone over x, this is just the cone over x1 union the cone over x2. Because the cone is just the set of all points whose in an plus 1 such that the equivalence class lies in x1 or in x2. And clearly also both of these are not equal to the cone of x, because otherwise xi would be equal to x. Obviously the cone over x is the zero set of the same ideal of which x is an ideal, so therefore it's also closed in the interval 1. Okay. So thus it follows that Cx is reducible, and thus it follows by the defined case that the ideal, or the defined ideal of Cx, which is the same as the homogeneous ideal of x, is not by the defined case. Okay. Now let's look in the other direction. So we assume that our ideal is not a prime ideal. Now, in some sense, it's clear that the argument should be the same as in the affine case. If it's not the prime ideal, we find two polynomials such that their product does not lie in the ideal, that their product lies in the ideal, but the individual ones doesn't. And then x will be the union of the zero set of the first one restricted to x union the zero set of the second one restricted to x, and that makes x reducible. The only problem that we have with this argument here is that we have to work with irreducible, homogeneous polynomials. So we have to make sure our polynomials are homogeneous. And so let's make that work. So assume this is not a prime ideal, then should follows there exists two polynomials f and g in k x0 to xn, which do not lie in the ideal of x, such that f times g lies in the ideal of x. So the power of these polynomials don't have to be irreducible, so they don't have to be homogeneous, so we somehow have to make them homogeneous, or to do some, get some homogeneous polynomials out of them. So we choose the numbers I and j minimal, such that fi, so the degree I part of f, and gj do not lie in IH. So I know that f does not lie in it, so there must be some degree I part which does not lie in it. and the same for G. And I take the smallest degree for which it doesn't lie in. So in particular, it means that all degree k parts for k smaller than I lie in the ideal of H. And so, therefore, I can subtract them from F without changing the fact that F does not lie in I and that the product of F times G lies in I. In the same way for G, I can take any part of smaller degree than J of homogeneous part of smaller degree than J of G. That part will lie in this ideal. So if I subtract it, this the whole polynomial G will still not lie in the ideal, but the product of the things with this part subtracted will lie in the ideal. Because subtracting something from the ideal, from inside the ideal, from a polynomial doesn't change the fact whether or not it lies in this. So the upshot is the following. So by subtracting the homogeneous parts of lower degree, so, from F and G, we can assume that these are the lowest degree homogeneous parts which are not zero. Homogeneous parts of F and G. But then I can, so in particular, I can take Fi times Gj. So Fi is the lowest degree homogeneous part of F. Gj is the lowest degree homogeneous part of G. So this product is the lowest degree homogeneous part of Fg. No, you can only get a term, a part of the degree I plus j if you multiply these together. So thus is the lowest degree homogeneous part of F times G. And now we use that the ideal of H is a homogeneous ideal. So as it's a homogeneous ideal, you know, if F times G lies in the ideal, also every homogeneous component lies in I. So as RH of X is a homogeneous ideal, and F times G is an element in IH, then also the part of degree I plus j, which is Fi times Gj, is an element. Okay. And so now we are in, now the angle becomes the same as before. So thus we can write x1 equal to did I want to do so the zero set of I union Fi and x2 equal to zero set of I, so union Gj. Then these are both closed subsets of X. So we have Xi in X is a closed subset. And this is the strict closed subsets because Fi, for instance, does not lie in the ideal. So I is Ix. Okay, in this notation. So Fi does not lie in the ideal of X. So that means there is some point in X where it does not vanish. So that means this set is strictly smaller than X. The same way here. So strict because Fi is not an element in H of X. And on the other hand, clearly, if I take the union, so as F I times Gj is an element in I have that x1 union x2 is equal to the zero set I intersected Fi union zero set Fi intersected Gj, which is the same as the zero set of I intersected zero set of Fi union zero set Gj. And this we know is the zero set of the product of the two. And this is just equal to the, so I was the, so this is the same as just the zero set of X because Fi times Gj is an and this obviously is X. So this shows that X is reducible. I've written it as a union of two strictly smaller closed subsets. Okay, so this was for the moment as much as I wanted to say about these projective varieties. Now we need to somehow, to go any further, we need to develop some tools how we can investigate our affine projective varieties. And so the tool that we want to look is somehow want to be able to look at maps between them. So maps that preserve the structure. And if we can understand enough about them, then we can do many things. So we want to talk about functions and morphisms. So we want to maps P from X to Y between say affine or quasi-projective varieties which somehow are allowed, which are compatible with the structure of quasi-projective varieties, which somehow preserve this fact, so which are compatible structure. So it's like, you know, in differential geometry, you would have that such a map would be a differentiable map between manifolds. In topology, it would be continuous map between topological spaces. Now we have to define what we want to mean by a map between varieties, which is compatible with the structure of a variety. Now, in some sense, there seems to be an obvious answer, which turns out to be not completely true. Namely, you know, these varieties are somehow zero sets of polynomials, which lie in some, and we are living here in some affine projective space. So the easiest answer would be that the coordinates of this, so if we have, for instance, if x is in AN and y is in AM, then we would want that, you know, that we can write, for instance, phi as f1 to fm, where the fi are polynomials. That seems certainly very compatible with the algebraic structure. Everything is in terms of polynomials. This is, in some cases, this is right, but it's not. In general, we have to do something slightly more complicated. But anyway, this is a good approximation. So we will first look at that. And before doing that, so, okay. So in particular, when we want to look at such maps between varieties, the simplest case are the functions. So a function for me is a map from a variety to K, or if you wish, a map from a variety to A1. So like, you know, in differential geometry, a differentiable function on a manifold, or a continuous function on whatever over there. And so in one way, one doesn't usually do it, but one way to define a differentiable manifold between a differential map between manifolds would be to take a continuous map which is compatible with the differentiable function, so that the pullback of any differentiable function is differentiable. We will also not do that, but that would be one way how one could proceed here. So therefore, we want to first look at functions. So let me, as a first thing, look at polynomial functions. Which are kind of a special case of the map. Then we will use them to make maps. So what would this be? So this should be just, so what we want this to be, this is a map F from X, which is some, say, in AN, a fine algebraic set. To K, which is given by a polynomial. So let me define this now properly. So definition. Let X in AN be an affine algebraic set. So what I call the coordinate ring of X is, I call it AX, and this is defined to be, I take all polynomials and I divide them by the ideal of X. Okay. So,
is this a square bracket or one's annotation on A?
No, well, no, in many cases one takes it, but I write A here and then I take a round bracket. I mean, in some books, maybe you have you would have, sometimes you have kx and kx for the field of rational functions, but the difference is, I prefer to have completely different letters. So as I put a instead of k, I think I'm allowed to put round brackets. Okay, so I mean, in every book you find a different notation. I choose this one, which is easier to write. Okay, so just as an example, so if the x, for instance, the zero set of y minus x squared, one can show that this is an irreducible polynomial, so it follows that the ideal of x actually will be the ideal generated by y minus x squared. So this is all equal. And so we get that a of x will be equal to kxy divided by the ideal generated by y minus x squared. And you can easily see that this is isomorphic as a ring or as a k-algebra to the polynomial in one variable. Why? No, because you can just you can write down the isomorphism. In this case, here, this coordinate ring is a very simple ring. It just is a polynomial ring in one, isomorphic to a polynomial ring in one variable. Okay, so now this a of x, we can either view it as such an abstract quotient, or we can also try to think of it in a more concrete way, namely as a set of functions on x, namely the set of all functions from x to k which are given by polynomials. So ax can be viewed as a set of functions. So I can just say as a ring of functions on x, namely either as a ring or maybe I should say, because we need that. So I usually like to say ring, but what I really need sometimes is k-algebra. So I just remind you that a k-algebra, so k is a field, a k-algebra is just a ring. For us, the ring is always a commutative ring with 1, which contains k as a subring. So a typical example is just, for instance, a polynomial. No? K is a subring as a ring of constant polynomials, and a homomorphism of k-algebras is a homomorphism of rings, which is the identity on k. So k-algebras are 1 and are 2 are k-algebras, so they contain both k as a subring, and so that phi restricted to k is equal to the identity. Okay? So it's not a big deal. You always have to, in our case, we always have something which comes from polynomials, and I usually say that something is a ring homomorphism, but what I usually mean is that it's a k-algebra homomorphism because it will always be the identity on constant functions. Okay? So now let me say definition. A polynomial function on x, so on x in N, say we find algebraic set or whatever, but it could be any subset actually, is a function, by which I mean a map from x to k. So of the form f is just the restriction of f to x, where f is a polynomial. Okay, so just we take a polynomial, we put any point p in x into it, and this gives us a map. I mean, the most stupid thing. And now, obviously, these form the K algebra. So we have the ring structure is just pointwise addition and multiplication. And obviously the k is just the constant functions. So so then we notice following Diploma, these are, so if I take this ring of polynomial, this K algebra of polynomial functions on x, this is the same as the coordinate ring, by which I mean there's a canonical isomorphism. So position, and so there's an isomorphism. Say the x is isomorphic to the polynomial function on x. So of K algebras, namely the map is just if I take the class of a function, so modulo the idea of x, this is sent to the function f restricted to x. And it's clear to just if I take this map f is sent to f restricted to x, this is clearly a homomorphism of K algebras. From K, from all the polynomials to the polynomial functions on x. No? So we just restrict it to x. This obviously is compatible with addition and multiplication, and so this is a homomorphism of K algebras. And what is the kernel? So first, this is surjective by definition, because we have defined the polynomial functions as precisely the restrictions of polynomials. So by definition, this map is surjective. And the kernel, what is the kernel? These are all the polynomials which are mapped to 0. So this is the set of all f in k x1 to xn such that f restricted to x is the zero. Is a zero function, which means that f lies in the idea of x, in other words. This is the idea of x. And so, whatever, if you wish, by the homomorphism theorem, this map gives us an isomorphism between the quotient ax, which is kx 1 to xn divided by ix, with this. Okay, so this is quite simple. But what this means for me is that in future I will identify these two things. So ax is identified with the polynomial function of x because they're canonically isomorphic. So I'm allowed at any moment to kind of, to kind of exchange between the two, either viewing it as an equivalence class or as a restriction of a function. And as you can see, that's really the same. Okay. So now let me see what comes next. So now we want to use these polynomials to make some morphisms, which, so those given in terms of polynomials are called polynomial maps. So polynomial maps. So let's see, so that x subset an, y subset an should be finite right sets. So then we define definition of polynomial map phi from polynomial map from x to y, well, okay. The map of the form so I just write this f1 to fm from x to y, which is given by sending a point p equal to a1 to an to 1 of p until m of p, which therefore is just given by putting the coordinates ai into the fi, and we have these n coordinates. This map is called a polynomial map. So for fi polynomials in n variables is called a polynomial map. So these are somehow the simplest maps you can think of. We just take an m tuple of polynomials, and the coordinates of the map in the image are just given by these polynomials. So we just put the coordinates of a point in x into all these polynomials. We have m polynomials. These give us the common coordinates of the image. Okay, very simple. So this is called the polynomial map. And then, say if so a bijective polynomial map will be called an isomorphism. No, that's not true. Whose inverse is also a polynomial. Is called an isomorphism. So, it's as usual, if you have maps between things, you call something an isomorphism if it has an inverse, which is in the same category. So, and in that case we see x and y is isomorphic. So one should maybe note that instead of polynomials I could also have used polynomial functions. So note that this field equal f1 to fn depends only on f1 restricted to x until fn restricted to x. So instead of saying that such a map is given by an m tuple of polynomials, I can also say it's given by an m tuple of polynomial functions. Thus, C is also defined by m tuple of polynomial functions. So this is all quite elementary. So let's look at a few simple examples so that one can also see examples. So for instance, I can take just a projection. So x from A2 to A1, which sends the point AB to A, is a polynomial map. Yeah. Of course, if I call the coordinates on this A2, x and y, it's precisely given by x. So I could also write the following if I take, just to see what the pits. So if I take t squared from A1, so let's say t is the coordinate from A1, and I want to view this as a map from z to y minus x to the 3. Now, so I could say, would this thing be a polynomial map? Well, the answer is no, because there's actually no such map. I mean, if I take the map t squared, it doesn't map A1 to this thing. It maps to A2, but the image doesn't lie in the zero set. So this is not a polynomial map. I mean, just because it's not a map. From A1 to this. Obviously, this thing is a polynomial map from A1 to A2, but here I'm asking it to be a polynomial map from here to here, and this is obviously isn't. So it's actually, I just say this because this is something, a mistake that people often make. They just write down something and don't worry where it will end up. No? If you say you have a map from A to B, it's better it should go from A to B. Let's look, so obviously we can use the same map from A1 to the zero set of y minus x squared. This is now fine if the second coordinate here is y, the first is x, and we see if I send t to t, if I send a point a here to a squared, then this is fulfilled, so this is a polynomial map. And actually, we can see it's an isomorphism. As you can see, if you take a restriction of the projection to the first factor, then it will give you back what you had. So the inverse is x restricted to 0, y. So we which sends a point, you know, A, comma B to A. Now, if you start here with the point A in A1, then it's sent to A squared, and you send it back to A. And it's also not difficult to see it works the other round. If you have a point in this zero set, so that means that you can write in the form AB, where A squared is equal to B, then you know, you can send it back here, and it is in the image of this. So one more case, we can also look at the zero set of y squared minus x to the 3. So if I just look at the real points, so this is a Caspary-Cubit. So the real points somehow look like this. And you can make a map here. So we have a polynomial map. T squared, t to the 3.
Things otherwise?
Yeah. No, I mean the first coordinate is for me x. I have to take the third power of x to get x to the 6, which is the same as the so yeah. So at least I want it like that. From A1 to C. So this is a polynomial map. It obviously maps to this thing, and you can see that this is bijective. Because if you know t squared and t to the 3, you can get back the t by dividing this one by this. So in fact, there's an inverse. The inverse map is just we take a point. So I just write it like this. If I take a point A, comma B, which lies in C, then I send this to B divided by A, which gives you back t. Obviously, if A is equal to 0, you can see the point when here, if you have a point here in this 0 set, if one coordinate is 0, the other one also has to be 0, and this only can happen if the t before was 0. So this is when A is different from 0, and 0 otherwise. So this is the inverse map. So you see, we have a bijective polynomial map from this to this, but this is not an isomorphism. Because this map is not given by a polynomial. Okay, so we see that it's, and in some sense it's also kind of clear if you think of it. So if you look at the real points, the Caspary-Cubit looks like that, and you know you have this map to this, and okay, it's a bijective map, but somehow to say that this is an isomorphism somehow doesn't seem right. No, I mean this point doesn't look at all like this point. Okay. But for instance, you know, this is a homeomorphism. No, I mean, with any topology you want. Okay, so these were these one of the examples, and now. So one thing that we can do if we have a polynomial map, we can use it to pull back polynomial functions. So if we have, we can take, you have a polynomial map from x to y. If you have a polynomial function on y, we can pull it back to a polynomial function on x. And it actually turns out that the polynomial map is determined by this pullback, which somehow makes polynomial maps between affine algebraic sets entirely a subject of algebra. There's no real geometry in it. So let's see. Definition. So that then x in En, y in En, the affine algebraic sets. And phi was given by some polynomials f1 to fm, phi polynomial map, which means that the fi are some polynomials in the x1 to xn. So the pullback phi upper star from the coordinate string on y to the coordinate string on x is defined by phi star h is equal to h composed with phi. Now, so it's clear. So what do we have to see? We actually have to see that this maps ay to ax. So no, if h is just an element in ay, so it's a restriction of polynomial equal to say h restrict y. Okay, so maybe the coordinates there I call y1 to ym, the coordinates on am. And then what do we have? So how do we get this composition? So I take h composed with phi of some points, say a1 to an. This is what? This is h of f1 of a1 to an until fm of a1 to an. So that means h composed with phi is just given by h of f1 to fm, where in kx1 to xn, where this is the polynomial which is in x1 to xn, which is obtained from h by replacing each yi by fi. So this h is a polynomial in y1 to ym. Now we just replace in each monomial the yi by the fi. H of f1 fm is the polynomial in x1 xn obtained by replacing each yi, so placing in h each yi by fi. Okay, because that's precisely what it means. So therefore, and then we have to restrict obviously to x, but then, so that means this is actually a map from AY to AX, and I mean, maybe I should say, why does it, so a priori, let me just see. Yeah, okay, so that's fine. So it's a map from AY to AX, and furthermore, we have to see, and furthermore, we see that it's a ring homomorphism, obviously, because if I take or in the homomorphism of K algebras, you have a constant function, it's pulled back to a constant function. Take a product of two polynomials, it's pulled back to the product of the polynomials. Okay, so there's nothing there. This is the point. And so the pullback is a K algebra homomorphism. So that's P star from 1 here is a K algebra homomorphism. Now we have the following theorem that this K algebra homomorphism actually determines the polynomial map. So that x in the n, y in the n, define algebraic sets. The map from the polynomial maps phi x to y to the K algebra homomorphisms from AY to AX, so the other way around, which sends phi to phi star, is a bijection. So we let me just first try to prove it. So that in some sense means giving a polynomial map between two affine varieties is the same as giving a K algebra homomorphism the other way around. So if you want the language of categories, this would imply that you take the category of, in this case, finitely generated K algebras together with K algebra homomorphisms is equivalent, but in a contravariant way, to the category of affine algebraic sets with as maps the polynomial maps.
We should add that these K algebras are integral domains as rings.
No, I'm not. In the moment, they don't have to be integral domains.
I mean, for it to be an equivalence of categories, we have to.
No, these are algebraic sets. They are not, algebraic.
No, on the algebraic side.
No, but in the moment I'm not requiring them to be integral domains.
But they are integral.
No, they are not. I have, if X is an affine algebraic set, then then AX is not an integral domain. If I want to restrict to varieties, then I would have integral domains, but I haven't told you that yet. And then I would, it would indeed be true if I take polynomial maps between affine varieties. These correspond to K algebra homomorphisms between integral to K algebra homomorphisms between finitely generated K algebras which are integral domains. Okay. But you know, no, it's not important. I don't like this. I mean, it's not important. You know, it's just if you. I know you kind of like categories. I don't really, but it somehow means there's. It somehow we're not really. We're really doing just algebra. We're just talking about this. So let's talk. Let's do it. So maybe we'll want to sketch the proof. Phi from x to y be a polynomial map. Then we have, so then phi star from ay to ax is a K algebra. So we want to find the inverse map. So now say that phi from ay to ax is K algebra. I have to find the polynomial map so that the pullback by this polynomial map is phi, and also anyway. Okay, so now where should this come from? There's actually some. It's actually quite simple. You only have to observe one thing, which I maybe will say, you know, instead of having it come out as a miracle. So if you have, so assume we have polynomial map. Phi from x to y, so phi, which is given by f1 to fm from x to y, and we take now yi, the restrictions of the coordinates on an to y. Am to y. So this lies in am. No, I just take the coordinate function. So these are some elements in ay, and what would be now? What is phi? If this is phi, what is phi star of yi? What I'm supposed to do is I'm supposed to take this yi, replace. You know, I take, for any polynomial in the yi's, I'm supposed to replace the yi by fi, and then take the corresponding polynomial. So I get that phi star of yi will be fi. So that means I can reconstruct our polynomial map by just looking at the pullback of the coordinates. And so now so this was just, so therefore let me just do it. So this was just as I wanted to motivate it. No, I mean it's not a deep fact, but no, one doesn't have to make it a miracle. You know, it's the obvious idea, and then one should also say it. So let y1 to ym in ay be the coordinate functions. So by which I mean that if I now write say large y1, so if this is the polynomial ring in which if these are if I now call the variables on am, y1 to ym large, so if for y1 the variables on am, you have that yi is equal to yi restricted to 1. So that's, I mean by coordinate function. Okay, so then we see And so let these, and so we put Fi to be phi of y, according to this, because this phi is supposed to become the pullback by this. So, what?
We take a representative of Fi.
Yeah, now we take a representative, so we don't really have to, but we take a representative of Fi. So let Fi in kx1 to xn with Fi restricted to x is equal to Fi. So for all I. So then what? Then if I take F1 to Fm from x to Em, this is a polynomial map. Now, obviously, we want this to be a polynomial map from x to y. So we have to see that it maps x into y. So, to see it maps x to y. Then it's a polynomial map from x to y. So why is that? So let H be an element, maybe we should write it large, in the ideal of Y. Then, if I take H, so I call this thing phi, then what is H composed with phi? This is H of F1 to Fm which is equal to this. Which is the same as phi of H of y1 by m. So it's a representative of that. So, but what is this? So y1 to ym are the restrictions of the coordinates on am to y, and h, so where h is the so if I take if I restrict the coordinate to this, and this lies in the ideal of y. If I take an ideal, I have something in the ideal of y, and I restrict it to y, so this is 0. Okay, so thus we see that thus we have that the image phi of x is contained in the 0 set of the ideal of y, which is y. And so this is indeed a map from x to y. Now I had to, obviously I had to avoid that I have this counter example which I had before. So I have to see, whenever you want to say that you have a map from somewhere to somewhere, it should go from somewhere to somewhere, not somewhere else. this is fine. So now we have to see, so we have this map, so we have the map that to phi I associate to a polynomial map phi I associate phi star was one map, and the other one phi star. So phi was a polynomial map, and on the other hand to phi yeah, now here I just called it phi. I associate this thing which I called phi. So this, what was it? The polynomial map which is given by phi of y1 and phi of ym. I want to show that these maps are inverse to each other. So in particular, we have to, there are two directions. I only will show one. So, for instance, if phi is given by f1 to fm, where these are polynomial functions, so where the fi elements in Ex, then if I do this thing, if I take this map phi of y, so if I take now the pullback with, so this is given by this, so I can first look at the pullback by this, and now I apply it to y1 this map from x to y. So I first associate to phi the pullback, and then I do this construction here. Then this is just f1 fm, as we have seen. So this means that this composition is at least the identity. So, so this composition is the identity. Maybe the other composition I leave to you as an exercise. Okay, so to show that if you start with a homomorphism, and you take the morphism, and you take the polynomial map given by this, then the pullback by that is the homomorphism to start it with. That's not more difficult than this, but we can do it for that. Okay, and maybe as a corollary, I should say we have that the polynomial map P from x, y is an isomorphism if and only if P star from AY or X is an isomorphism. So it's a standard thing. Once you have a bijection between the morphisms, so the morphisms, also the polynomial maps and the homomorphisms, then you get that isomorphisms correspond to isomorphisms, because what does it mean to be an isomorph? It means that it has an inverse. And so if you have, so you want to have that the inverse so if you take the map, compose it with the inverse, it is the identity. Now you can take the pullback of the map and compose it with the pullback of the inverse. This will be something. And the other thing you can take is the identity. And as you have a bijection, these have to be the same. So if the and vice versa. Okay. No, I mean anyway, it's a standard thing. Whenever you have this bijection between, it's a formal consequence of the fact that you have this bijection between the polynomial maps and the homomorphisms. That isomorphisms correspond to isomorphisms. You can solve that. Okay, so now we have. Okay, so that was as much as for the moment I wanted to say about these polynomial maps. So now one could think, so if we only want to deal with the fine algebraic sets, then we could be happy with these polynomial maps, but we want to look at more general things. In particular, later we will want to look at projective algebraic sets and projective varieties. And if we wanted to, it's not difficult to prove. If you want to say well, so if you have if you want a polynomial function on a projective variety, you can show that this always has to be constant. And so if you want to use polynomial functions to define maps between projective varieties, then all maps map one projective variety to a point in the other projective variety. That's not very exciting. So we need something more general. I mean, you don't have to understand why this property is true. We will see it later. But at any rate, for the moment, I just say that polynomials are not enough. So we need to look at more general things. And so we want to use this. So now I want to study so again, somehow morphisms, which are maps compatible with the structure between, say, affine and quasi-projective varieties. And it turns out that polynomial functions are not enough. So we want to give them again in terms of functions, but they are not enough polynomial functions. So we have to look at something slightly more general, and so the next more general thing is to look at rational functions. You just take the quotient of two polynomials. This will give you a function which is defined everywhere where the denominator does not vanish. And we will find that these serve our purpose. So we will use rational functions. So f divided by g, where f and g are polynomial functions. Okay, so let's see how we do this. And here, to make my life a little bit easier, from now on I will assume that I'm working with varieties, that is with irreducible things, because then these rational functions is just the quotient field of a certain integral domain, and so or the fraction field. So that's something we already know how to do. One could also work in the case when these are not irreducible, then one has to talk a bit more carefully about localization, but I prefer to do it this way. So definition So first I still do it in the defined case, so let X in N be closed subvariety. So remember that variety means it's irreducible. So it's an irreducible defined algebraic set. So we recall the coordinate ring. AX, which is the polynomial ring divided by the ideal of X. And now, as this is a closed subvariety, we know that the ideal of X is a prime ideal. Therefore, this A of X is an integral domain. Like you wanted before already. And so, so that means, in particular, we can form the fraction field like we have done before. So the function field function field or field of rational functions on X is just the fraction field is the fraction field, the field of fractions, whatever. So K is denoted Kx, and we had said this was the fraction field of Ax. So this is a field. In fact, it is some field extension of our original K, but usually by transcendence. Okay. So an element of Kx is called a rational function on X. So for instance, if we know that the field of rational functions on An is just the quotient field of the polynomial ring, which we had seen was just the field of rational functions in x1 to xn. So we had this before, just the quotients of two polynomials. Okay, so maybe one, however, so okay, I called this thing rational functions, so they should be functions. So a function is a map from x to k. So we want to see that this is at least more or less a map from x to k. And so let's see how that, in what sense this is true. So elements of kx define functions, well, not on the whole of x, but on open subsets of x. So open in the heuristic world. So how does this go? First, I will not have Wi-Fi. Let me introduce the local ring. So we if I take a point P in X, then the local ring of X and P so it's denoted OXP. This is all the rational functions, so quotients of polynomial functions, such that the denominator does not vanish at P, or at least so that we can write it in such a way. So this is set of all elements H in Kx, which we can write as follows. So there exist f and g polynomial functions such that we can write h as this quotient of f divided by g, and g of p is not 0. Okay. So obviously, if you have a quotient, so in the quotient field, in the fraction field, an element here can be written in many ways as a quotient of two functions. I can just multiply both with the same thing. So what I need is that there is a choice such that the denominator is not 0. But in future, we will be a little bit less careful, and we just write the same thing. OXP is the set of all f divided by g in Kx, such that g of p is non-zero. So this just means that it's all elements in Kx which can be written as f divided by g, such that g of p is non-zero. Okay. Line is up, so let me see what I can say. And then I can at least say so for an open subset, the ring of regular functions on U is defined to be OU, which is just the intersection over all P and U of the local ring of X and P. So this intersection takes place in Kx. No, this OXP obviously is a subset in Kx. So it just means that it's all the rational functions with the property that for every point P, I can write them as f divided by g, such that g of p is not 0. It does not mean that I can write them once and for all as f divided by g, so that this works for all p and u. It could be that for different points in p, I have to find different representations. No? That's what I say. No, I just write this. So we say that an element h in Kx is defined at P, or if you can write h equal to f divided by g with g of p non-zero. So, in other words, equivalently, if and only if h is in the local ring, that's it. So we say h is defined there, and so in other words, this O of u can also be written. This is the set of all f in Kx, such that f is defined at all p in u. And now the point is that such an f is, if f is in OU, it defines us map from U to K. So then with that I want to stop. So regular function H in OU define maps and or functions, I always call them, if you go to K, functions, which I also call H, from U to K. Well, what would the function be? It's the obvious thing. So a point P in U is sent to f of P divided by G of P. You know, if H is equal to f divided by G with G of P not 0. Okay. And now, maybe I will anyway have to review this a little bit. So you can check for yourself, but I will maybe also briefly do this. Well, maybe I can also do this now. It's very easy to see that this is well defined. So obviously, H can be written in many ways as a quotient of two elements in AX. And if I do this in two different ways, then I want to see that we get the same result. So this is well defined. So if H is equal to f divided by G, and it's also equal to f prime divided by G prime, with G of P is different from 0 and G prime of P is different from 0, G of prime of P is also different from 0, then what does this condition mean that they are equal? It means, according to the definition of the equivalence relation which defines the fraction field, it means that f G prime is equal to G, or say f to f prime G. So that's the definition. And so we can put P into this, so it follows that f of P, G prime of P, is equal to f prime of P, G P. And so we bring this to the other side, so it follows that f of P divided by G of P is equal to f prime of P by G prime. So that means our definition of these functions were defined. H from U to K is well. Okay, so maybe I stop here. So we have defined these regular functions as rational functions, which are defined somewhere, and we can see that this actually does give a map. It's not just a formal thing. And so, okay, next time we use these, and then well, you'll see. So we see each other on Monday already, I think. And I'm not yet quite sure. So maybe I can stop.